How was I supposed to know that?
That's from Chem. Actually, that's what AP told me.
Oh, you guys think I like paid attention again?
Are you gonna find?
This is like so curved,
Are
bro.
you gonna find?
You know, like a 60 to get a 5. You know how low the bar is for me to get?
You know how low much lower it is for physics?
Yeah, it's crazy. I don't know people do that.
You need a 30 to get a 5.
Okay, I could see.
That's something like that.
No, it's the 40 something. That's basically no distinction between something like a 40 or like a 100.
Hey.
There's like 70% vibrators passing.
I think 3% pass rate is all right.
It was a vibrator.
Fire rate was 21%.
More people got a 5 than got.
No, it's all the years that
It used to be 41%.
in 20, this is 2020.
The year before was 37.
That's all. But this year is the lowest.
Check music theory.
Check our history because I forgot to forget. No one's a better art historian.
Very clear.
Hey,
That was me. Wait, no, I was the last year. What was the one?
Oh, it is.
This stuff.
All right, let's do the last 16%.
6.5.
There's just something else there.
No, I think because they change.
They're like,
They have to do that.
like you guys are.
So I remember that one HR scheme was really.
I was on my exam and I didn't know what the fuck. So I was like all prepared to because it was like both a two or something. And I just started just looking at the Taj Mahal and I'd be like, oh, yeah, the truth contributes this. And it was like on the show. I got it. Fuck. The truth, yeah, oh, the truth contributes. You got it. Go ahead and start. Like basic history, I know a couple of art pieces. By a couple of 250.
Wait, that's the. Oh, I had this. I had that question on my practice. Like,
Yeah, it's on the
This
price.
was really easy if you like did this. And just do it.
Floors, how it is.
160. Divided.
what do you know this calculator?
Like, because the percent dissociation is so high.
No, this is the only time you can. Yeah. I got 0.0. Is that right? Oh, I
I know
can't.
0.018.
Yeah.
Figure.
I probably did it wrong, but I still.
So, any questions before we get started today? So on the board is actually questions that I received multiple times. And I feel like I did not explain this one clear enough. So I want to actually take this time to explain. I hope you haven't had to explain yet. I'm sorry, I'll actually improve this one in the future. Okay, so there are actually two types of questions I want to go through at the beginning of today's lecture. Okay, so this is actually one of the percent dissociation problems that you will actually encounter in your practice exam. Okay, so this is actually one type. There's actually another one. I don't know whether everybody have this one. The KB, actually calculate KB of a conjugate base. From these things, they don't use the term called percent dissociation. They use a term called ionized or non-ionized. Okay, so how to handle a question like this? Okay, so let's start from this one. This one is actually somewhat similar to one of the example we went through in my question list. Okay, so let's read the things carefully. It says at a certain temperature, the percent dissociation. Okay, I guess this actually some word we actually get used to it because it things like in the data bank right now they use this word a lot, ionized or non-ionized. Okay, so it says the percent dissociation ionized, these two words are equivalent. So we actually get used to it. Okay, so it says the percent dissociation of this weak acid in lake concentration is 10%. Okay, so you want to calculate Ka, right? So the question is actually want to calculate Ka of this weak acid. Okay, and the data is that this weak acid concentration is 1.63 m. Percent dissociation is 10%. Right, so in the past, the way I teach you guys is that starting from the definition, right? So what percent dissociation means is actually your proton concentration over your weak acid concentration times 100%. That's the definition of percent dissociation. Okay, so and then for weak acid, that we always assume we can use small x approximation, right? So this equation will become the square root of weak acid concentration times your Ka divided by your weak acid concentration, right? So this whole term can be rewritten as this whole term times 100%, and they will still equal to your percent dissociation, right? So if you're starting taking this route, okay, so what you're going to get is the weak acid concentration is 1.63. Ka is the things you want to actually find out. Divided by your weak acid concentration times 100, they give you a value of 10%, right? Therefore, you know, this 1.63 times your Ka should equals to 1.63 times 10 divided by 100. Okay, which this give you a value of maybe just 1.63 times 10 to the negative 1 power. Okay, and then you square on both sides so that you have 1.63 times your Ka is going to equals to 1.63 times 10 to the negative 1 to the second power. Okay, therefore your Ka can be calculated as 1.63 times 10 to the negative 1 second power divided by 1.63. Then we end up with the answer of 1.63 times 10 to the negative 2. Right? So this actually, if you follow what we actually went through in the past, that's the number you're going to get. Okay? But later on, you'll realize that you don't see this number. I believe this is actually multiple choice questions. Okay, so you actually don't see this number. Okay, and then you'll realize that the correct answer is actually 1.8 times 10 to the negative 2 from your multiple choice options. Okay, so these two numbers are very close, but not exactly the same, right? Why? Huh? No, so I want to actually focus on this. When can we actually write this? When can we actually write the photon concentration equals to the square root of weak acid concentration times your Ka? When can we do this? When you can use small x approximation. Okay, so when can you use small x approximation? It's when your Ka is small enough. Okay, so how small is small enough? Simple is actually smaller than 10 to the -4. So if you look at this, Ka, if you calculate it using this way, what's the exponent? It's -2, right? So there is some deviations. That's why you don't get the exact number. Okay, but still, this number will be actually very close to your answer, right? So you can still actually use in this way to quickly identify what will be the most reasonable answer to select. Does that make sense? Okay, so the next question is actually how do you actually get the exact number from your practice questions, right? That means actually you cannot use small as approximation, right? Then what do? You go back to your ice table again. Okay, so I'm going to show you exactly what you should do if you want to get the exact number. Okay. So you have a weak acid. It's going to dissociate, right? And then you know the Ka will be defined as proton concentration over your weak acid concentration times 100%. So in the beginning, initially, you have your HA, its concentration is 1.63, right? And it's going to dissociate a certain amount to produce this and that. Okay. So let you know when you reach equilibrium, you're going to have 1.63 minus x. This will be your x, there will be your x. Okay. So in here, it tells you the percent dissociation equal to 10%, right? That means your proton concentration over your weak acid is 10%, right? Which is 0.1. Okay. And if you look at here, that actually tells you your x. X is actually representing your H plus, right? So your x is going to equals to 0.1 times your weak acid concentration. Okay, so you know your proton concentration is this. Okay. And then your A minus concentration is also X, right? That means actually A minus is also 0.163. Okay. And then since the Ka, this is Ka, not the percent dissociation. Since your Ka means this is now, okay, let me write these things. Okay, so your Ka is actually, if you know the proton concentration, A minus concentration at equilibrium, okay, divided by your HA concentration equilibrium, right? So then you know at equilibrium, your weak acid concentration will equals to 1.63 minus 0.163. Okay, so this will be your HA concentration. This will be your A minus. This will be your H plus. Right, so you actually have all this information. Therefore, you can actually calculate your Ka from this. Okay, so by doing that, you're going to get a value of that's actually how you get that number. Okay, specifically. Okay. So, all will be the fast practice to actually get you the correct answer. I say all will be the ideal, right? But what's the problem of ice table? Very small, right? So I would still suggest that try the original method first, okay? Because no matter what, even though the small x approximation is not 100% valid, you can clearly get your Ka quickly, okay? And then the number, compare the two. One is 1.63 times 10 to the 2. One is actually 1.8 times 10 to the 2. Right? Error-wise, it's around 10%. Okay, so even under the situation where your small x approximation is not valid, you can still get the answer that's actually very close to the true answer within 10% error. I think that's actually still very good. Okay, and if you go back and look at all the options that you have, you should be able to see the answer was actually specially designed. They're actually pretty different. Okay, so you can get this 1.63. That's looking for the number that's most close to how you get overlay. Okay, then this will just take you some time. But of course, you feel like I really want to get that perfect numbers. That's fine. Like go back to your ice table and do it slowly. Does that make sense to everybody now? Yeah. So this is actually a couple of things I did not actually really explain in great details, but that's all the things that you know. Is that clear? Any questions for this? You good? Okay. Next one. Next one is going to get you even more confused. Okay, determine the KB of a species. Okay. In a 0.23 n of this solution, the base is 11% unionized. Okay. So when we say this word ionized, unionized, okay, you again go back to the concept of percent dissociation. Okay, but it's very difficult for us to think about this because we only handle the percent dissociation question for weak acid. This one is actually a conjugate base, right? So how do we actually proceed with this type of questions? Okay, so first, still define our question, right? We want to know the KB of this weak base. I will use A minus to represent it. Okay, that's the things you want to actually solve. Okay. Data, you know your A minus has concentration of 0.23 m, right? And then the non-ionized percentage is 0.0034%. Okay, so those are the information that you get. Okay. So how do we actually handle this? Okay. So I'm going to give you a pretty long explanation starting from the weak acid, go all the way to here. Okay, so stay with me. So previously we know if you have a weak acid, once you dissociate, you have H plus your A minus, right? And then we will write out the Ka equals to H plus times your A minus divided by your HA. Okay. That's actually the definition of the Ka of a weak acid, right? So how do you define the Kb of a weak base? That means actually you need to actually write your A minus first, right? If you want to look at your conjugate base. Okay. So how do you write the equation? The equation to write is actually your weak base A minus is going to interact with what? Yes. That's actually a very important concept that you can have. Okay. So your weak base interact with your water, end up with the weak acid plus OH minus. Okay. So how do you write your Kb? Will be HA times OH minus divided by A minus. Right. Water by itself, pure liquid, doesn't go into your expression of the equation. Okay, so if you add up the two, what do you get? You add up this weak acid, weak base equation. What do you end up with? Did you notice that this and that you will cancel out? This and this will cancel out, right? So what do you end up with? H2O become H plus plus OH minus. Okay, what's the equilibrium constant K? It's actually your K. Right? So we also learned that if you add up two equations, you can write a new equilibrium constant equals to the product of the two equations. Right? This is actually why we can always calculate Ka from Kw and Kb. Okay, so we use these things a lot, right? Kw equals to Ka times Kb. We always use this one in our previous calculation. That's the main reason. Okay, so this is actually a complete equation sets that give you the specific equation that allow you to actually calculate your Ka from Kb or Kb from Ka. Okay, so this is actually the things I feel like I did not actually elaborate enough. Okay, but right now I hope this become more clear. Okay, so going back, so in the questions, what it says is that the non-ionized part of your weak base is this 0.0034%. Okay, so we want to actually pull out this equation and take a look. Okay, so you're going to have A minus plus H2O. They give you HA plus OH minus, right? And then you know the initial concentration is what? 0.23, right? And then the ionized species, that's the things you want to actually recognize what it's actually talking about. Okay. If you look at this equation, which species is actually non-ionized? This is definitely ionized, right? Water is actually not something that's relevant. Okay, so you only have two more left, right? Either your HA or OH minus. We all see that OH minus is charged species. So that's another thing it's talking about. It's talking about what? This guy, right? The non-ionized species is your HA. Okay, so it says it's actually 0.0034%, right? That means actually your HA is what? We can actually still use the ice table to solve this. This will be 0.23 times 0.0034%. Right? And then you're going to get the same number for your OH minus. Okay. So then you can use the ice table way to solve this. Okay, so that's actually one way to do it. Okay. But in order to actually make the way we solve problem more consistent, right? I would still suggest that if you can understand what I say, that means percent dissociation wise, you know is OH minus over your A minus times 100%. Okay. And then your OH minus concentration will be your A minus times your KB divided by your A minus times 100%. Okay, and here we know the dissociation percentage is 0.0034%. Okay, then you plug in your A minus concentration. In this case, is 0.23, right? So square root 0.23 times your KB divided by 0.23 times, okay, I cancel out this, right? 100 equals to 0.0034. Therefore, you know, 0.23 times your KB is going to be equals to 0.23 times 3.4 times 10 to the 1, 2, 3, negative 3 divided by 100. Okay, then you get the square root out on both sides and then divide by your 0.23. Okay, I actually have a number here. So this is actually 7.8 times 10 to the negative 6. Okay, then you take the square on both sides. Then you solve your KB is going to equals to and this will give you a value of 2.66 times 10 to the negative 10. Okay. So, what's the thing that we have to remember? The thing to remember is that if today you have a conjugated base, okay, A minus, if you start from there, what it says the thing is actually non-ionized percentage. Okay, we go back to the percent dissociation equation again. Okay, and then we try to put that ionized ratio into that percent dissociation place. Okay, so we put in this, right? Even it says actually non-ionized. Okay, you can actually see that no one is actually tell you the percent dissociation. Okay, then you just go back to the original calculation mode to solve your KB. Okay, does that make sense to everybody now? Yes. This one, no, this is actually the student sent me a screenshot. The student sent me the screenshot of the questions. Yeah. So the only thing you can do is actually go back and watch the videos. Screenshot the video and practice on your own. Okay, make sure you actually get familiar with the concept here. Right. The things we did not went through in the past is that we did not specifically talking about when you have a conjugate base. Okay, and then it's non-ionized ratio. How do you calculate the KB? Okay, so this is actually a new type of questions I feel I cannot really cover from my lecture. Right. Okay, so let's actually how you should solve this. I hope this makes sense to you. Okay. If it doesn't, then watch a couple of times, then I hope that will actually eventually you can actually internalize all these things. All right. Okay. Any other questions for this? Okay. So if not, then today, I guess today will be actually a shorter lecture because I know most of you want to get back and re-study for your midterm too. Okay. So I will actually tell you, we're not going to go through many questions today. Probably actually not. Okay, we just tell you about some of the concepts, okay, that you should know for chapter 16. Okay, so chapter 15, we actually enter the era of thermodynamics. Okay, so anybody know this topic, thermodynamics? Okay, so thermodynamics is one of the hardest topic for undergraduate student, I would say, because it's actually very abstract. Okay, so anyone know that the three laws of thermodynamics? What's the first law? Conservation of energy. Everybody got this term? Okay, so energy will always, it's not going to disappear. You just actually change the form that it exists. Okay, so for example, we have an apple on the tree. Okay, once it ripe, it's going to fall. Right. So what's changing the energy? Form. Right. We actually write something like that high up. What kind of energy do you have? Potential energy. Okay. So once it falls, the potential energy transform into, yes. So everyone has some sense actually, right? So thermodynamics is actually a subject that scientists observe or we see in our daily life. Okay, and then to figure out how many different forms of energy we have. Okay, so how many forms of energies do you know? Apparently we know the potential energy, right? Kinetic energy. What else? What's thermal energy? Heat. Good. Anything else? Light is like a wave of energy. Yes. What else? Nuclear. Yes. Any other things?
Electric.
Okay, so thermodynamics is actually a thing that's start to describe how this. That's actually one very important one you can actually even mention. What's this force? Chemistry, right? Yeah, chemistry energy. Right. What's actually the term that describes the chemistry energy? Delta. Something wrong with that. What's actually the typical term we use to describe the chemical energy? Huh? Yes, delta H. Okay, so do you feel confused about what is chemical energy? Where does energy come from? See, you are still Chem 1, right? How come your professor did not tell you this? What's wrong with your chemical professor? Okay, so let's find really simple things. Okay, I want to see the things because once you see it, it's actually interesting.
Yeah.
Okay, if you don't make it, you're like, oh gosh, it's actually another thing I have to remember, which I'm going to forget very soon, right? So by now you should actually have a good idea. Okay, when we say okay, we have a material, what is actually material matter? You learn this. You have this element table, right? So the smaller things we talk about typically is actually what? Atoms, right? So when atoms actually got together, you have molecules. Okay, when a bunch of molecules got put in together, you have materials. Okay, so you have to have like clear hierarchies. Okay, things actually building up. The smallest building block for us is atoms, right? And then molecules. And then you have a combination of molecules. Okay, and when we talk about the nuclear energy, right? It's actually energy at the atomic level. Okay, what is atom made out of? Oh, it's K1. So what's inside your atoms? Really? Okay, neutron and proton and very good. So these are three major things that you have, right? Okay, so think about the charge. Okay, so remember the model that we have is actually electrons doing what? It's surrounding around your neutron and proton, right? Your neutron and proton formula are core, and then your electron orbits around that. That's actually the model that you guys have learned from your Chem 1, right? So nothing about a very simple questions. Okay. What happens when you put a positive charge and negative charge close to each other? They're going to snap to each other and kill each other, right? That's how you neutralize things. Okay. Then why our atom doesn't do that? Now you say the electrons orbiting your nucleus, right? Your nucleus is actually a positive charge, and electrons stay surrounding, but not doesn't actually goes into your proton, right? It's actually dissolved. Okay, so that's actually the area where you have these nuclear temperatures. Okay, explain you why that's actually the case. Okay, there's actually a very strong force actually between your nucleus and electron. Okay, they repel each other somehow. Okay, so when we talk about the nuclear energies, that's actually where it happens. Okay, this actually very, very small. Atom is pretty much the smallest one you can have right now, right? Okay, so let's actually talk about all this nuclear energy. That's actually the domain you're actually talking about. Okay, then you have molecules. Molecules actually just have multiple atoms. They start to actually form chemical bonds. How do the atoms form chemical bonds? They share their electrons in between, right? We call it covalent bonds. Okay, so for example, H2. Okay, proton has how many electrons? One electron. Okay, we're going to talk about this a lot in chapter 18. So that each proton going to donate one electron, so they form this, they actually let the electron resonance between the two, and then they form the bonds. Okay, and they store the energies within that bonding, within that electron resonance between the two atoms. Okay, that's all we mean the chemical chemistry energy. Okay, we actually break this apart. Okay, when you actually burn something, it's actually breaking bonds. Once breaking bonds, the energy goes somewhere. Okay, so that's why we have these energies. Okay. Yeah, so if you have many atoms that connect to your covalent bonds, then you have larger materials. Okay, so if you actually are a material scientist, then you learn how all these energy level changes. I have different combination of structures. Okay, it's actually very cool knowledge, I feel. Yeah, if you have chemistry major, then you are going to learn more things. Okay, so a lot of this actually within the things you're actually looking at, right? So once you have molecules, things actually get a lot more interesting, right? You're going to start have this so-called electronic transition energy, rotational energy, vibrational energy. Okay, and those things actually describe the behavior of a collective quantum entity that have many atoms. Okay, the granular structures. Okay, then once you just start to move, then you have different energies associated with it. Okay, and then beyond that, we move the things from bottom to the top. It is why we talk about the potential energies. Okay, so all these is actually all connected with each other. Okay, so scientists actually spend many years, pretty much 200 years now, okay, to observe all these phenomena and try to understand how the energy flow from one form to another. Okay, and then after observe many things for extended time, then they come out with this subject called the thermodynamics. Okay, where they found out some simple rules that we can use to predict if something is possible to happen or not. Okay, so this is actually a very interesting concept. Okay, and why would you care about one thing will happen or not? Okay, because you are not going to waste your energy to pursue something that's impossible. Okay, so this actually the things that I guess 200 years ago, that's something that people care a lot. Okay, because actually really use their effort, their energies, their strengths at the correct topic so that we don't waste our energy. Okay? The same thing is going to happen to every one of us. And we can make a choice. You will wish that you know, okay, is this going to work? Is there any chance it will work? Right? If you know there's actually no chance, then you don't even bother to actually pursue. So that you don't waste your time, right? It's the same thing, the same concept happened to your thermodynamics. Okay. So if you found the things that say is interesting, that maybe I should take thermodynamics, then you may be able to see more for the specific perspective. Okay. So we're talking a lot of things, right? But the first topic we're going to introduce for this chapter is something called entropy. Okay, so the things that we are actually very familiar with is actually entropy, right? Delta H. We're going to introduce you the other term for the entropy. Okay, anyone heard of this term, entropy? Yeah, randomness. Disorder, right? This is actually what you have learned in the past. But how does that make sense to you? That's all, it's the same. I learned the same definition for the entropy when I was young. Of course, I just think it. I don't really actually think about it. But after I become a professor, I started to question everything. Okay, so how does it actually make sense to you? Why the randomness will tell you something's going to happen, more likely to happen or less likely to happen? How does that make sense? What would be the physical picture after that? Right? Does that make sense to you? If I just tell you, okay, if something is actually more random, it's going to happen more likely. Does that make sense to you? If you're more sloppy, your Jenkins grade will be better. Does that make sense to you? Doesn't, right? So why actually scientists try to explain this things to you that way? My explanation is that because they don't see the most important part of that definition. Okay. Now you're lucky because I'm a PChem professor, so I can actually tell you something more, which is actually everything in the textbook. Okay. So these are actually more updated definitions that I hope you will make sense to you. Okay. Entropy describes the possibility of a certain event that can happen. Okay. So does everybody play this game called Marble Run? Everybody know what to think about the Marble Run? So basically you have a marble and you hit it, and then on top you just have a bunch of columns that allow it to fall. Right? So everybody understand what other things I'm talking about now? Okay. So when you do this marble run, okay, when you do it actually 1,000 times, what do you find? What's the possibility that you are going to have? That all the ball is going to fall into each column. You realize that things is actually not random. Right? Everybody played this game before? This marble run game? Ever? No? Really? Gosh. Generation gap, huh? Oh my gosh. Okay, so you can do this at home. You can create these things very easily. Okay. So if you do these things.
Yeah, that's
Okay. So if you consider, okay, every single column dictate a individual events. Okay, so once you did these things, that it is actually randomly formed, then every single color shall have the same probability to get your model, right? But if you think about this, let's say there's actually some events that occupy two columns. We call it event A and event B. Okay, so one have two possibility that will lead to your event A and 5 possibility related to your event B. Okay, so then you think your model, which one is more likely to happen? B, right? See, everybody's actually taking it easy. Of course, it's B, right? Then now we actually think about what the color means scientifically. Okay, so the answer to that is that we use something called entropy to describe how many ways that something can actually happen. Okay, so the larger the entropy, then it's actually more ways it will happen, right? And put into an energy perspective, that means actually you have a system that more ways to storage your energy, then it is more likely to happen that way. Okay, so if you actually get back down to a very simple probability concept. Okay, when we talk about the randomness, what it means actually, since it's random, means actually many ways to make it happen, right? To make your room become messy, there's actually 10,000 ways to make it messy, right? But to make it neat, there's only one way. Does that make sense? Yeah, therefore, it's a lot more likely your room is actually more messy than neat. Okay, so again, come back to this probability concept. Okay, so everybody follow me, okay? Okay, we're going to go back to the molecular level now. Come back to the atoms, come back to the molecules. Okay, so we talk about different kind of energy, right? So a few simple rules that we know. When you have a gas molecule, okay, let's just use water as an example, it's easier for you to think. Water, okay. So water can exist as a solid, liquid, and gas, right? Okay. Which one is actually the most rich one? Solid, right? So when you have a solid, what does it mean? It means actually all the atoms tend to actually align one by one in a very specific way. There's actually not much freedom over there. Okay, I just need to just stand right next to my neighbors and continue. Right, that's what solid means. Okay, so under the case, can I be actually have a lot of variety to deposit my energy? It's not going to give you that much freedom, right? When we go to water, okay, what's the difference between solid and water is that when you become a liquid, the distance between your atoms they become further apart, right? So everybody can wiggling around, right? Then I have actually some ways to store my energy. Therefore, the entropy for your liquid will be much bigger than your solid. Okay, so which phase will give you the largest entropy?
Yeah.
Yes, right, because you don't have neighbors, you just do whatever you want. Okay, that's why you have the largest entropy. Okay, that's actually the first thing that we want to learn. Okay. That's actually the first things we're going to talk about today. Entropy of material in different phases. Okay, so gas phase is always the one that gives you the largest entropy. Okay, so one type of question you're going to see in this topic is that I give you two substances. compare which one has a larger entropy. Right, so the first thing you do is actually looking for the one that exists in the gas phase. That's your answer. Okay, very simple, right? So now I want to think a little bit more. Okay. Everybody know what helium is. Helium is a gas. Okay, it's a monoatomic gas. Okay, so what kind of energy do you think it can have? It is not very clear, right? It's a single atom. It cannot vibrate. Right? And then it's center symmetric. So this means actually nuclear theory is actually rotating around. Right? So the only thing you can think about is actually maybe some electronic transitions, but it's actually normal gas. So it doesn't really happen either. Okay, so there's not much things you can do. Okay, there's actually not many ways you can create positive energy. Okay, now I want to compare that to another molecule called hydrogen. The gas form too, right? But right now you have two atoms. How come we have two atoms? You can start with this. What's this? You vibrate. Okay, so you have a way to store your energy through the vibrational energy. Right, I can vibrate really fast, really slow, doesn't really matter, right? But there's actually one way to store your energy. Okay, what else? I can start tumbling around. That's your rotational energy. Okay, so essentially one energy level your hydrogen and helium has is what? They can move around. Right, let's call the sometimes we call kinetic energy, sometimes we call it translational energy. Okay, so apparently H2 is a lot more complicated than your helium, right? So the more atoms, then your vibration mode will actually increase drastically, right? So if that whole is the gas form, then you look at which one has more atoms, right? The more atoms is going to give you a larger entropy because you have more way to store your energy. Okay. But let's have the same atoms. For example, if you have HBr and HCl, which one is going to give you more energy? To have more way to store the energy. The answer is actually the heavier one will give you more way to store the energy. Okay, so it's very simple because the heavier one is going to give you more electrons. Okay, and then if you have more electrons, then different combination of that will give you more way to store your energy. Okay, so this actually is section one we want to talk about. It's actually very simple, right? Both is actually who is actually gas. Okay, so you have gas, okay, you are the winner. But if the two you compare, they're all in the gas form, or all in the liquid form, or in the solid form. Okay, then you have to think about how complicated your molecule is. More atoms, more ways to store your energy, right? The heavier the atom, if you have the same amount of atoms, the heavier molecules have more way to store your energy. Okay, so I hope this actually makes sense to you because once it actually makes sense to you, then you're going to actually memorize it. Okay, which makes your life a lot easier. Okay, so with this simple concept, we can solve this already. Okay, so one more HCl and one more HCl, which one have larger entropy? Right, first thing is actually check out their phase. Also that they are in the gas phase, right? Therefore, you know it's not going to use the phase to determine which one has larger entropy, right? Then you start to look at which one has more atom. You realize both of them have the same atom. They're all diatomic molecules, right? And then you go down to, okay, who is actually heavier? HBr is heavier than HCl, therefore will be your answer. Okay? That's very simple. Okay, then the other question I'm going to ask you. Okay, they give you one equation and ask you, does your reaction or product have larger entropy? Okay, then the things you need to do is actually start to count the number of gas molecules on both sides. Okay, whichever side has larger number of gas molecules, then this actual side going to give you a larger entropy. Okay, so if you look at the left, how many gas molecules you have? 3/2, right? And if you look at the right, you have 1 plus 2, which probably is 3 gas molecules, right? Therefore, you know the product side has larger entropy. How about this one? 1 mole of NO2 gas plus 1 mole of N2O4 gas. So both of them is the gas form, right? They start to count which molecule have larger number of atoms, right? That's why you pick N2O4 for your answers. Okay. So, any questions so far? I want to actually think about this. Okay. Think about if I tell you the entropy is just a representation of resistance. If less things I teach you, how are you going to solve this question that we just went through? It becomes very difficult. Right? How do you actually see the randomness of molecule? There's no easy way for you to see that. Right? But if you put it into a perspective that the entropy is just the ways that the molecule store your energy, then suddenly you have actually a very simple and easy way to comprehend the question we just went through. Okay, so I hope this actually helps you to understand this concept, which is very, very challenging for many of the undergraduate students for thermodynamics. All right, I hope I make it sound actually simple and interesting. All right, so the next things, we want to go a little bit deeper. Okay. I guess I'll stop here for today, so everyone can go home and prepare your midterm too. Okay, but I know you guys are busy. Okay, after the midterm too. Okay, we're going to actually finish all the remaining content for these chapters. Okay, don't worry about it. And the rule of thumb of the things that I observe all the time is that midterm 2 is actually the one that we're going to get the lowest grade. Midterm 3 is actually the one we always get the highest one. Okay, but as long as you understand the concept, it will be easy. Okay, so make sure I check. Do well for your midterm 2, but come back strong on Thursday. All right, so that's it for today. Thank you.